Section 8.3, exponential functions. Something to remember is to let b be any real number such that b is greater than 0 and b cannot equal 0. Then for any real number x, a function of the form y equals b to the x power is called an exponential function. The big B represents the base value, x is your exponent. So in example 1, it wants us to approximate the expressions round to the 4 decimal places. So it says 8 to the radical 3. So this is basically using your calculator. The way you're going to write it inside your calculator, and I'm going to show you a breakdown, is you're going to hit 8, and on your calculator you have a little caret key. For those that don't have it, you'll see a little hat, and then hit the parentheses key. You're going to hit 3, depending on the calculator you're using, you can write 3 and then hit the square root key, close the parentheses, and you're going to get your answer. So I'm in my calculator. I'm going to go 8, and then here's my little caret key, hitting the parentheses, and then I go 3, but I'm going to hit the square root key. See, now it's after it. Depending on the way your calculator is set up, you need to change it. So I need to delete that back. I'm going to put square root, hit the 3, close the parentheses, and hit equal. I get 36.6604. It said to go 4 decimal places, so we're going to write 36.6604. And the reason I don't go anything after it, because after that 4, there was another 4. And remember, it said 4 decimal places, so 4th place here. 4 does not make it go up, so that's where we end up with 36.6604. Again, the next one says 5 to the negative radical 17. So same situation. 5 caret, in parentheses, you're going to write negative, hit the square root key, put 17, close it. So when we do that in the calculator, we get, we're going to go, it was a 5, so we're going to go 5 caret, parentheses. I'm going to hit my minus key, just because that's what's going to happen to be. Square root, 17, close the parentheses, hit equal, and I'm getting 0.00131 is what I'm going to write down. So I'm seeing 0.00131. After the decimal place, there's 1, 2, 3. There's my 4th decimal place. The 1 did not make it go up. So you end up with 0.0013 for your answer. When you look at the next one, it's square root of 10 raised to the radical 2. So we're going to have, hit the square root 10, caret, parentheses, square root 2 closed. So square root 10, caret, parentheses, square root 2 closed, equals, and we get 5.09456. So we see 5.09456. Again, we need to go 4 decimal places. So here's 1, 2, 3. Here's my 4th. Now that 6 is greater than 5, which makes the 5 increase. So you end up with 5.0946. Okay, property of graphs of f of x equal to b of x. So exponential function is defined by f of x equal to b to the x power, where b is greater than 0 and b does not equal 1. So in this graph depicted here, first thing I notice is the graph lines do not drop below the x-axis. What does that mean? It means, remember, you're bound by 0. Your b value has to be greater than 0. So when we look at our situation here, you approach 0 axis, the x-axis here, the 0 line, but you don't go below it. So The pink line you see here says the b value is greater than 1, which means that base value was greater than 1. So it's a 1.1, a 1.01, a 3, a 5. So it's getting larger. The blue line that is decreasing here, notice that it's coming from the left, going down to the right. The values of the b fall between 0 and 1, which means this is where you will see your fractions, your below $0.1 values. You approach 1 and you are not 1. 0, 1, which is your y-intercept because it's hitting the y-axis, is your bound line. That is your boundary point. Most graphs will cross through the 0, 1 if it's in the base form. So some rules that you need to know. If the b value happens to be greater than 1, it's called increasing exponential function. So we know it as our exponential growth. Think of your economics classes. If the 0 is less than b less than 1, it's called the decreasing exponential function, known as exponential decay. Again, think of your economics classes. Also, think of decay as in when you're doing chemistry values. Finding the half-life of radium or nobelium, any of those type of equations, that is what exponential decay means. It's approaching 0. Exponential growth, it means it's going to positive infinity. Exponential decay is approaching 0. Remember that. Next thing we need to know is the domain. So domain means the x value. So it's going to be all reals, negative infinity to positive infinity. And if you look at the graph here, notice that that graph line has arrows, which means it's still increasing for the x's to the left. It's still going x's to the right. Same thing with the pink. X's to the left, pink to the right. They're still going large. Range is going to be between 0 and negative infinity. So remember, we didn't cross below the y-axis, so we are going positive direction. The line y equal to 0, it's known as your x-axis. That is your horizontal asymptote. Function passes through the point 0, 1 because f of 0 is the same thing as saying b to the 0 power, which is 1. Okay, so we're going to try some exponential growth and decay. So it says graph the functions. It says f of x is equal to 2 to the x power. So remember, you can refer back to a t-table. So I'm going to make a little t-chart. And notice, we want to have negative numbers for the exponents and positive numbers for the exponent. So I am going to pick... I'm going to go from -3 to +3 on the x's. So you do your t-chart. -3, -2, -1, 0, 1, 2, 3. Not necessarily will you'll always have to do these. I'm just giving you a boundary so you can see what's going to happen. So we're plugging in -3 in here. So it's 2 to the -3 power. Remember the rule. You're not allowed to have negative exponents. So you make it a reflection of it. So this is actually 1 over 2 to the 3rd power, which makes it 1/8. When you plug in -2, same thing. It's 2 to the -2. A reflection is 1 over 2 squared, which is 1/4. 2 to the -1. 1 over 2 to the 1st, which is 1/2. 2 to the 0. Remember, anything to the 0 power is 1. 2 to the 1st now. 2 to the 1st, that results in a 2. 2 to the 2nd gives you a 4. 2 to the 3rd is an 8. So here are our values, and we're going to plug them here. So when we look at our graph, when x is -3, the y value is 1/8. So it's just a little bit above the line. When x is -2, I'm at 1/4, so I'm a little bit beyond that. When I'm -1, I'm at halfway point, half the distance. When I'm at 0, I hit the y-axis at 1. When x is 1, I'm at 2. When x is 2, you're at 4. So that's 3, 4. When x is 3, you're at 8. 5, 6, 7, 8. So what's happening is that your graph is going positive exponent, exponential growth. Remember the domains, it's going to be negative infinity to positive infinity. Your range values, notice we did not get below 0, so we're from 0 to positive infinity. Okay, we're going to do the same thing, but now we're going to show decay. So it says g of x equals 1/2 to the x power. Again, create your t-chart. Because it's 1/2, think of, so I'm going to use -3, -2, -1, 0, 1, 2, 3 again. So when we plug in -3, so it's 1/2 to the -3 power. Remember, the rules that we learned back with exponents. Negative exponents, if you have a fraction inside, you are flipping the fraction and making the sign positive. So we're going to go and write this as 2 divided by 1 to the 3rd power. Well, 2 cubed is an 8. Here we have 1/2 to the -2 power. Again, think of it as 2 over 1 to the positive power. So 2 squared now makes that a 4. 1/2 to the -1 power. We're flipping it, so it's 2 over 1. Now it's positive 1. Well, 2 to the 1st is still a 2. 1/2 to the 0 power. Remember, anything to the 0 power is a 1. Here we have 1/2 to the 1 power. We have a 1/2. 1/2 to the power of 2 means we square the numerator and denominator and we get 1/4. 1/2 to the 3rd power means 1 cubed, 2 cubed, so you get 1/8. So we have our values that we can draw our graph with. So again, we're starting with -3. When x is -3, we are positive 8. So we have a dot up here. When x is -2, we're at 4. When x is -1, we're at 2. When x is 0, we're at 1. When x is a 1, we're at a halfway point. Then a quarter point. And so forth. So we are decreasing. We are exponential decay. Again, the domains do not change. Domain is negative infinity, positive infinity, your range. Again, even though it's 0 down here, remember, 0 is positive and your still y-axis is positive. So we are going from 0 to infinity. Welcome back. We're continuing 8.3 with example 3, applying an exponential decay function. So in this example, we're given, it says, in a sample originally having 1 gram of radium-226, the amount of radium-226 present after t years is given by, and they gave us a formula. It says A of t is equal to 1/2, which means half-life, raised to the t over 1,620, which represents the years, where A is the amount of radium in grams and t is the time in years. So A says, how much radium-226 will be present after 1,620 years? So first thing, you're going to write your equation. It says A of t equals 1/2 t over 1620. That is a generic equation they gave us. This will be used repeatedly for the next 3 parts. So they want to know it's present after this amount, 1,620 years. So the t value is being replaced with 1620. So when you go to your equation, I'm writing 1620 in the parentheses because that's what t is being replaced with. So 1/2 to the 1620 divided by 1620. Well, 1620 divided by 1620, that's about value of 1. So I get a half. But what does the half mean? Remember, we started out with 1 gram of radium. We now have half a gram of radium. So in 1,620 years, we've done a half-life. We've halved the amount of weight that we started out with. So now we're going to find, B says they want us to find how much radium-226 will be present after 3,240 years. So again, our equation, A of t is 1/2 t to the divided by 1,620. And we're replacing the t with now the new value. The t value for this time is going to be 3240 is what we're replacing it with. So we have A of 3,240, 1/2 of 3240 divided by 1620. Well, that numerator value is actually double the bottom value. So we're actually looking at 1/2 power of 2. Well, a half raised to the power of 2 means 1/4. So it means we have 1/4 grams, which is 0.25 grams left of radium. What do you guys think will happen when they want us to find how much radium-226 will be present after 4,860 years? Remember, it's half-lives. The base value here is a half, so it means you're doing a half of the previous value. So in this instance, our t value is now 4,860. So we have our equation, A of t, 1/2 to the t over 1620, which is 1/2 to the 4,860 divided by 1620, which the numerator happens to be triple the denominator. So we're actually looking at 1/2 raised to the 3rd power. That is actually 1/8 grams, which is 0.125 grams left of radium. So exponential functions are often used to model population growth. Suppose the initial value of a population at some time t equal to 0 is p naught, which is our initial value. If the rate of the increase of a population is r, that's represented by r, then after t years, remember t has to be in years, the population p of t is given by, and they give us an equation. P of t is equal to p naught, which was our initial, times the parentheses 1 plus r, which was our rate, closed to a power of t. So in the situation that you will know your initial and you will know your rate. They will give you a time frame as to how you want to use it. So in example 4, it says applying an exponential growth function. It says the population of the Bahamas in 2008 was estimated at 321,000 with an annual increase of 1.39%. So it says find a mathematical model that relates the population of the Bahamas as a function of the number of years since 2008. So we kind of already have a base value of what our mathematical model is going to look like. I am going to use the equation that I wrote out here, our initial. So we know that our mathematical model, P of t, is P naught times 1 plus r raised to the t power. But that's only a generic formula. And this one is saying that the population in 2008 was estimated at 321,000 with an annual increase of 1.39%. So we need to identify specific things. The 321,000 happens to be our P sub 0 or P naught. That is 321,000. Then they tell you our rate. It's an increase of 1.39%. 1.39%. But you're not allowed to use percents because if you think in banking situations, they don't use the percent, they use decimal form. So you need to change this to decimal form so you can either divide by 100 or move the decimal place back 2 places. So I'm 0.0 2 decimal places, 139. 0.01, because if I multiply by 100, I move over to the right 2. If I divide by 100, I move to the left 2. So this is our R value right here. This is what we're using for R. This is what we're using for P naught. So it wanted us to find an equation that we can use. So P of T stays as is because we don't know how many years. Our initial value was 321,000. So you're going to write 321,000. And in parentheses, you're going to write 1 plus 0.0139 to the T power. You can consolidate this piece right here to finalize your equation as P of T equaling 321,000, 1.0139, because you're just adding the dollar to this, to the T power. This is my mathematical model. Since we found our mathematical model, we can now try to figure out what it says, hypothetically, if the annual rate of increase remained the same, so we're keeping the same rate. Use the model from A, which we came up with, to predict the population of the Bahamas in the year 2025, round to the nearest 1,000. First thing we need to remember, in our original problem, this is the number of years since 2008. So the year 2008 represents T of 0. That's the first thing I need to remember. We need to get to the year 2025. So that is going to be how many years after 2008? Well, if I add 17, I get to 25. So that is 17 years. So then we are going to write our equation. P of, instead of a T, I'm going to write 17 because it's going to be 17 years after the fact. So 321,000, 1.0139 to the 17th power. Okay, so we're going to plug this into a calculator. And remember the rule of thumb, there's parentheses here. So you're going to write 321,000, parentheses of 1.0139, close it, caret 17. So in the calculator, you write 321,000, parentheses, 1.0139, close it, hit the caret key, type 17. So I'm going to bring my calculator over. And we're going to write 321,000, parentheses, 1.039, close it, hit my caret key here, and hit 17 because I want to raise to the 17th power, and then hit equals. It says the population in 2025 should be 615,133. Remember, you don't have 0.4 of a person, you can only have whole people. So I'm going to go with just whatever's to the left of the decimal point. So 615,133. So our population is going to be 133,000 people.